Amanda Rousseau, and I'm here to talk to you about PE binary classification pitfalls. This stems from when I used to work with Hiram at Endgame, and we, looked at the training sets, and I had to verify, what's good and what's bad. And so I wanted to talk to you about those, but in the perspective of the reverse engineer. So a little bit about myself. I currently work at Microsoft. I focus on VR, fuzzing, and the Windows OS. Looking for vulnerabilities. I love spending time in IDA, so I'm pretty happy. I used to speak at several different conferences, Black Hat, RSA, DEF CON. As Hiram mentioned before, I used to be on the Facebook's Red team. I worked at Endgame doing malware research. FireEye, worked a lot on the hypervisor rule set. DC3, the DoD Cybercrime Center, doing a lot of forensics. I've been around the block, but I find happiest when I'm in IDA. I'm currently a DEF CON CFP reviewer, so I use a lot of my volunteer time to help with that. I currently teach malware RE on my website for free, so if you want some refresher workshops, you can do that. I follow fashion trends and occasionally post on Twitter. I've been trying to do less of it, but who has time, right? So let's talk about PE binary classification. What makes it so hard? So we have all of these bytes that we have to make sense of. For you, you may have a different visual of what you want to tackle, but for me, I see it as more of a pattern. And when I say that, I see things very visually, like visual patterns. So here's an example from BinViz.io where they take apart the bytes of the PE and display them as different shades of color. And over here, you can see just by knowing and looking at it and knowing PE files, I can tell that these black areas up here in the corner is a PE header. And this is NTDLL. That exe or DLL for this, it kind of looks benign in this area over here, this blue area. This is references or tables. And then we look at the second file, which is ransomware. It looks pretty normal in the beginning. And then you have this whole extra section here, which is executable code. Obviously, this must be another binary hidden within it. So I find that very interesting that if you're looking at data visually, and I'm assuming that these are the types of things that people want to take apart, for instance, with static feature extraction, binary slicing, PE header content, and the disassembly itself. So let's talk about binary slicing. We'll go back to that image. It's just basically taking slices of the binary data and making sense of them in some type of model that you want to train with. You can have, major blocks, major sections within the PE, but it's based on the bytes, right? So what's the downfall with this? And I'll get back to that. And now the PE structure, let's take that whole PE structure and make it horizontal, right? And we want to switch back this way so we can visualize it better. So there's different sections, and this is pretty common with, analyzing malware, even with signatures or heuristics. We're going to focus on, say, potentially malformed image optional headers. Import address table lives here, and maybe there's certain imports that are important. Like for instance, if it's going to call message box versus it's going to call create process. And then the data section, this is kind of jumbled blobs of data that are going to be used, these strings, completely large blobs, encrypted data, who knows? And then the text section, this is where all the code lives. So obviously we want to do some type of binary slicing or, focus on the functions here. And then finally, any non-standard sections, for instance, if you're using a UPX packed file, it's going to have an extra section just for the UPX code to live. And then overlay. So this one is not a very common term, but what it means is at the end of the file, they tack on a bunch of bytes. Usually this is a secondary payload of malware. So moving on. Now the disassembly. So there's two types of disassembly. One is the linear type of disassembly. Basically, it goes from linearly disassembling each instruction. This is what you see in like the disassembly tool Radari, Capstone. They're all focused on going one instruction at a time. And then secondary is the control flow. I think you're familiar with this, IDA. I think Binja does this as well. They're focused on the control flow. So what happens is it follows every jump and branch, call, loop, and return instructions to form these code blocks, which in turn makes the functions and builds that function table for you. Now, the downside of this is that when you do control flow disassembly, you're not going to find these weird functions that are not used in the static analysis or in the flow. So in static analysis, that becomes really hard to pick up if you're trying to do function analysis, especially if they're using threading or any type of asynchronous callbacks. And I'll talk about that. Oh, here's an example of control flow blocks. You can see for every jump and branch, there's going to be code in between. And even in VR, we call these code blocks. All right, so now the pitfalls. So what makes it so hard? Well, we've got packing and compression. We have encryption. We've got trash code insertion. We have compartmentalization and metamorphic code. And I'll go through each of these so that you can get a sense of what these are. All right, so I like doing diagrams, and if they're purple, it's great. So we have packing and compression. So what that is in the main code, there'll be a pack section of code that it wants to put into a new memory section. It does like a virtual alloc or create memory mapping and then try to allocate some space to put the bytes. It has this decompression loop. And as I'm saying this, this is what I see when I'm reversing. I see the creation of the memory space. I see the decompression loops. It'll loop like, a million times until it can put the code over there. And then it rebuilds the import address table to update all of those locations where the code is going to go. And then it changes the memory section to RWX so that it can execute that new memory section. And then it finally jumps into the entry point in the new memory section. So this is pretty common for packers. It's also common for compression or any type of like self-extraction. So what makes it difficult is that, you're doing static analysis on the binary itself when in turn it actually unpacks itself in runtime. So obviously there's going to be this disconnect in what the actual usage or methods that it does. And so packing is used by both commercial software and malware, believe it or not. UPX is probably the most common out of all of them. And, most of the time when you're doing binary classification, there's like this gray area for packers because you don't know if it's good or bad. And then binary entropy for compression or section are basically useless because it's just compression. If you can make sense of that, good for you. That's a good model. But I would suggest avoiding that. And stripped import address table is not representative of behavior. And what do I mean by that? When I'm looking at binaries, the first thing I look at is like what the imports are. Because that kind of gives me a sense of what it's going to do. But if something is packed, obviously the import address table doesn't exist or hasn't been rebuilt. So we're focused on, and this is what the import address table actually looks like. It's basically like in runtime, it gets allocated the actual address of where all of the functions live. And so when you're doing analysis on this, it's obviously, missing a lot of portions because where those functions go. And then after unpacking, it rebuilds the AIT table or the import address table. So if you're going to use that as a feature, it's probably not a great feature to use if it's packed. All right, encryption. So there's different levels of encryption. There's string encryption, there's data blobs, there's function level JITting, which I find fascinating. So strings can be polymorphic. Say you have like this obfuscation tool set that the malware author uses, and it can compress or encrypt strings on compile time. So every single time is going to have something different. Whole data blobs, same thing. If it's got an obfuscator, it's going to change everything, change all the bytes. And then function level JIT. I've only seen this in a very complex malware or APT level malware. And let me explain. So basically what it does, I guess I can go back here. Basically what it does is it allocates memory. Did I talk about it? Yeah, function level encryption. It allocates memory just like I explained before. It's going to have its encrypted code tacked on the end. It'll have the scratch pad of where it's going to have executable memory at, decrypts it and puts it in there, executes it, and then destroys it. And so it constantly does this to avoid antivirus or any type of like in-memory introspection. So this is really hard to catch statically, even dynamically, but it's very fun to reverse. All I have to say is, with something complex like this, hopefully there are other features that can, help against encryption. All right, trash code insertion. I like this one. So some of these are generated at compile time, kind of like the LLVM obfuscate. And I'll talk about some of those techniques. It's used by commercial software and malware. A lot of the times, these more complicated obfuscators are actually expensive obfuscators that commercial software uses. Basically, it's an insertion of NOPs to disrupt the disassembler or emulator if you're going to do emulation. And what does that look like? So here's an example of using AVX instructions to break unsupported disassemblers and emulators. So sometimes, they don't have the AVX instruction set. So obviously, it's going to have a really hard time looking at the instructions in between the actual instructions that it's using. So everything in purple here is all NOPs that is meant to disrupt any disassembler, automated disassembly that doesn't support AVX instructions. And that was Loki bot. All right. Useless functions that look legitimate. So some of the things that I found is bypassing ML sets is graphics and UI. So I found that if malware authors insert graphics and UI libraries or functions that just do nothing, it actually changes. It bypasses as benign because of if you have so many legit looking functions in there, maybe it's like changing the way your model is going to look at it. Okay, and then register reassignment. This one is fun. It's basically taking all of the registers that you usually use for like maybe the function arguments and switching them to different registers. For instance, I think, what is it, x86 64-bit, they use, it's like is it RSI, RDI, R8, and R9? One of those. It'll switch it to like maybe R15, R14, or something like that. And it'll change the way you're trying to look at functions if you're looking at this disassembly. All right, instruction expansion. This one I find really fun. This is what LLVM obfuscate does. Basically what it does is it's expanding certain arithmetic routines. For example, here it's expanding multiply into multiple different instructions. So you have kind of like this weird, obscure way of just trying to do a multiply. And then splitting large integers. Like for instance, say they wanted to split the address of one of the malicious functions or Windows API calls they want to use, and they split it up into two different integers, so that if you're looking at it in the disassembly, it's really hard to pick up unless you're doing symbolic execution or emulation. You're not going to be able to catch that. All right, and then control flow expansion or flattening. Basically what this means is You have a normal control flow, you know, your regular code blocks, your branches, your jumps, your returns, and instead, like a tool called Modificator will take this data and make it one big long instruction, like a linear disassembly for you. And it doesn't really tell you anything. It's just like one big long, you know, amount of disassembly instructions. So if you're reliant on code blocks, it's kind of useless. Or maybe it's not, maybe that's an anomaly, but just so you know that it exists. All right, another one is compartmentalization. What do I mean by that? I mean multi-stage malware. So let's say there's stage 1 droppers, downloaders, installers, self-extractors, all of these like first level malware binaries don't have a lot of techniques in them because their main focus is to get that second stage in the environment. Now, resource extraction, I think I kind of explained it a little bit earlier with compression. Basically, it has some type of resource or compression blobs that exists within it, extracts it and uses it. So obviously, it's really hard to see that type of thing. And then side loading. So side loading means you could have like some type of package or installer or a zip file that has multiple files within it. And you need that secondary file to be loaded in order to do the malicious thing. So if you're pulling data from VirusTotal in order to fill your data set, you're probably getting only a part of it instead of like the whole package that it was delivered with. So you have like this contextual information that you're missing. I feel like I'm blocking it. All right, and metamorphic code. So this is the code that only runs at runtime, and it changes the bytes in memory or the bytes on disk. So for instance, like I mentioned, dynamic AIT rebuilding, or rebuilding the import address table. For instance, they don't have any imports at all except for NTDLL and kernel 32. So they want with PEM, the process environment block. So what is this block? How many of you heard of process environment? Not very many. So this contains a linked list of all the different processes within the OS and Windows OS. And what they do is they find the first address of where this environment block lives, goes to the PEB loader, the inload order module list, and tries to find kernel 32 or whatever, you know, DLL that it needs in order to find and rebuild the address table by looping through all of those different functions that it needs and rebuilds it. Or they're just going to call load library and load the DLLs that they want. So this is very common in ransomware. This is very common in, I feel like the people that write this is probably using a kit that somebody else wrote. And you can tell because it's very different. More advanced malware uses this. All right, this is just a visual demonstration of what is actually happening. All right, and then self-process hollowing. I've only seen this in more APT level malware or, you know, bigger rats that, you know, have more code in them. So what it does is it extracts a code key from the main RWX area. And because some antivirus, they'll look for a virtual alloc or virtual protect to change the protection of the memory space. And they're looking for the executable flag. So what this does is they just extract out the bytes from existing executable memory space and then places their code with their malicious code within it so that, you know, it can execute fine. And then run once. This one I find interesting. The malware Upatre does this. So believe it or not, when Upatre runs the first time, it edits itself. And by the time it gets to VirusTotal, it's actually the edited version. So there's more samples of the edited Upatre version in VirusTotal than there are the first instance of it. So your training set has already worked at that point. I don't see this happening very often. It's mainly for commercialized malware that I've seen this, but it exists. So I would be wary of, you know, the data that you're pulling from VirusTotal. All right. Now we're going to dynamic feature extraction. So what if static doesn't work? Obviously, we need dynamic to get around packing, to get around some of these pitfalls that I explained before. So what does that lead us to? We're doing Windows API calls. We're training on that. We're looking at the function blocks again, because instead we're following it and as it's executing, or even the stack trace. Maybe we're just interested in the functions that are being called, in what order or what sequence. So let's talk about those pitfalls. Or actually, how do you extract them? So we are limited to virtual machines or hypervisors, emulators, and symbolic execution. So there are pain points with those systems as well. So let's talk about those. The first one is environment canaries, and this is pretty common, and I'll explain that in the next slide. There's asynchronous callbacks, trash code insertion again, it's a little bit different. Import address table hooking and manipulation, and API unhooking. That one is fun. I haven't seen too much of it, but it happens. All right, so first, environment canaries. What I find fun is the counters and time checks. Let me focus on this one first. There's UI traps, looking for the foreground window. If there's any windows that if there's any windows that exist, it's mainly checking if there's a user there or not. Because if you're doing a headless virtualized environment, obviously there's going to be no display, so it's kind of useless at that point. Exceptions and interrupts, hardware and memory traps like CPU, heap, and BIOS, file system and process traps, VM and debugger artifacts. And I'll go through all of these in the next couple slides. All right, so counters and time checks basically is to detect if there's any significant delay in execution. So if you're doing any type of debugging, I actually need a water. There one. Thanks. Thank you. Okay, the goal is to find significant delays in execution. So what do I mean by that? Either it'll call the RTDSC instruction, or it'll call us different API calls to determine that. For instance, get system time, get tick count, query performance counter, basically to see if there's any debugger attached or any virtualization that's causing it to hold up for any reason. It will just end execution right then and there. All right, UI traps. The goal is to determine if there's any headless execution. Basically checking if there's any like a display resolution, display dimensions, if there's any mouse movements. I've seen some hypervisors do this. Well, they'll just move the mouse around a little bit. Any existing UI windows. I think this is more for debugging, like determining if there's like immunity debugger or Ollie debug running, or if there's any windows existing, like let's see, like any of the sysinternals tools, something like that. And then exceptions and interrupts. So depending on your emulator or symbolic execution, sometimes the exceptions are not implemented. And so if there's no exception when they call, say, an in3 or an SCH, it's going to be suspicious. So it's going to expect that exception to be handled. But if your tool does not handle the exception, it's going to be suspicious of it and exit out of the process. Another one is checking the guard pages. I think this is mainly for debugging. If there's no page violation, it's going to say, hey, and this is mainly for symbolic executors and emulators. If there's no page violation, it'll just say, oh, well, I'm not really running in a proper environment. I should just exit out. All right, hardware traps. This one is interesting because it's just checking the hardware environment. Does it have BIOS information that it recognizes? Maybe it knows it's running in VMware, or maybe it's in VirtualBox, and it goes and checks those in the BIOS information, the registry. Uses the CPU ID instruction. Sometimes the CPU ID instruction is not implemented in symbolic execution, so you'll have to be mindful of that. Checking if the process heap has force flags. Sometimes, if you're running in a debugger, this is not set. So just be mindful of what environment you're executing in. All right. So with file system traps, the goal is just to determine where you're at. It's kind of like guardrails for, am I running in a virtual machine or not? Or is this like one of those machines that analysts use? So it uses mainly looking at known registry keys, known guest agents. It'll look for DLLs of drivers, kind of like the mouse driver, or maybe the VMware mouse driver, or any like custom drivers that it's aware of. Any virtual devices like pipes, network shares. Say you're like moving data from in and out of the VM to like check and analyze the malware, right? You have some network share, or even adapt names. They're pretty standard for a lot of virtual machines. All right, process traps. This is to determine what processes are actually executing, or if it's executing it in the correct way. So one of the biggest ones is knowing, well, down here, I put them in the wrong order, is checking the parent process. So if you're executing as malware, like a user executed, it would have explorer.exe as the parent. But if you're executing with like cmd.exe, obviously that's kind of sketchy. So it's going to check to make sure that it's actually running based off of what a user clicks versus what the automated analysis does. Checking, I'll go down from the top there. Known guest agent processes. So it'll go down through the PEB and try to look at all the processes that are being run, or it will, try to see if any process is attached to it. That's another one. And then checking if there's injected or loaded DLLs. This is very common for EDR. This is very common for AV. What will happen is in a suspicious process, it will inject its own good DLL into any process, and this DLL will try to hook APIs within that process to determine if the actual events are happening or heuristics. Sometimes it'll just like walk the PEB and loaded modules to see what DLLs are being loaded and figure out what shouldn't be there. All right, and then asynchronous callbacks. I find this one interesting because this is the main pain point for static analysis. If you're having like, say, any threading, obviously we go back to that call graph there, where there's a function that was not analyzed based off of the control flow disassembly. In a threading environment, you're given a address to a function that's going to be executed. So obviously this is not going to show up on the control flow graph. Same with UI callbacks. Sometimes I've seen malware, they'll use like a message box or a GUI window, and in the actual API call, you can like submit a function as a callback. Instead, they just have their malicious code as the callback and execute it that way. So it has to have like this rare instance where this UI window comes up and the callback gets executed. So it's really hard to find those things dynamically. And then network dependencies. Like I explained before with compartmentalization, if you have a dropper, the dropper is going to go call out to its command and control wherever its download server is. If the server doesn't exist anymore, obviously you can't get that secondary payload. So if you're analyzing malware that's super old, like 6 months old, even like 3 months old, or maybe even a month, you're not going to have that C2 infrastructure up anymore. You're not going to have that secondary payload to download. And even if you wanted to find it, you're going to have to be like, well, is this the right hash? does this go with this one? It's kind of like finding two pairs of socks. Same with these, well, not same, but IPC and RPC or COM and WinRT. So what are these? These are inter-process communication. So if it's calling functions that exist in either COM or RPC, you're not gonna be able to see that if you're only following the one process. If you're only injected into one process and extracting out the call graph from one process, you're not going to get the inter-process communication unless you're injected into all processes. So it's how you tune your virtualization environment to catch those things. And if your emulator or symbolic execution doesn't have that either, you're not going to catch that. All right, this one I find fun. Time bombs are really fun. I find this in a lot of bots. So what will happen is it'll either select a date or have some type of endless loop. Instead of having like a sleep call, it will sit there for like 5-10 minutes past the normal execution time of a virtualized environment. I think the average is like 180 seconds. So if you're doing 5 minutes, obviously you're not going to get anything because it's going to sit there and do nothing for 5 minutes. And I've seen the endlessly executing of like random functions that just do nothing. It's really painful to reverse. And then GUI functions that do nothing. I think this is, like I explained before, they're just there to look legitimate, try to make you go down different code paths. This is common with guardrails. So basically it'll say, oh, am I executing in the environment that I want to? We actually did this when I was at Facebook, where I wrote this malware that would make sure I'm executing in a Facebook environment and not some other environment, to make sure that when it executes the malicious code, it only goes to my target and not some random person if they were to ever pick it up. So this is very common for very targeted malware, or maybe even financial institutions. Maybe they're focused on what the software is there. If it's not there, then why should I execute? This helps prolong the length of their malware getting by AV. So I think if you can just have one execution and reuse it for at least a month until they get discovered, that's a win for them. So it's mainly to prolong their existence. All right. AIT hooking and manipulation. So I find this pretty often. Overriding the function addresses with malicious functions. I've seen this happen in some ransomwares and crimeware. Basically what it is like they take a message box, for instance. In the import address table, they have the legitimate address to message box. And they take that and knock it out and use the malicious address of their function and put it in the address table instead. So anytime message box gets called, instead they call their malicious code. I've seen this in a couple instances, but this becomes very difficult for like runtime execution. If you're analyzing, you're just like, why is this malicious code happening? For static analysis, obviously you're not going to pick this up, so it's going to look benign. So just keep that in mind. Oh, yeah, trampoline. All right, and then finally, AIT unhooking. This is very rare. This is only instances where they're focused on getting around EDR and AV. What it is to combat user land hooking. So in user land, they have either an injected DLL or some type of process that hooks API calls or running process. And either what happens is they patch the AIT or they patch the function prologue. Even what is it? Anti-cheat engine to do this as well. They will focus on the AIT. And for patching function prologues, what happens is they go in and find the DLL in memory, and the beginning of the function they wipe out, like, what is it? Push EBP or something like that is like the first instruction, and they put a jump instead to jump to their code that they're trying to trampoline with. So what happens is, instead of to get around this, what they do, they manually load the DLLs to avoid hooking. So instead of using load library, they manually load it using like some DLL loader that they've written. They'll allocate virtual memory, make it executable, put the DLL in there, do the same thing that the load library does to get it up and running, and then execute it. So obviously the hooking code is not going to catch that, so that they can get around the hooking. Another thing is repairing the AIT, going in and changing all of the addresses in the AIT to be the legitimate ones again, and then either runtime patching of the hooks in memory. So like I said, if they're patching the function prologue within the memory space of the DLL, they'll go in and they'll check if there's any difference between the file system one, the file system DLL, and the one in memory, and they'll say, hey, these two don't match, I'm going to overwrite with the good stuff. So that happens sometimes. Common with EDR though. All right, so key takeaways. So it's the reverse engineer's job to help verify the data for the training sets, right? Good data sets come from correctly gathered features, and it's good to have that close relationship with the reverse engineer to share some of these techniques and anti-analysis techniques that makes it harder for either static or dynamic analysis to work. And then secondly, how robust is your feature extraction or the tools are? For instance, like I said, if you're in a virtualized environment, how do you get around environment keying or environment enumeration? Or, are you running headless? Or are there things there to get around sleeps? Like, do you have to short circuit them? Some of these things is about hardening your analysis environment or hardening your disassembler if you like, say you're not implementing the exception handling. Does your disassembler or emulator handle that? Or you got to look into these things. And then contextual information is key. Like I said, static analysis alone is not going to help with these more rare features, like, or not rare, but packing and encryption. You're going to have that dynamic aspect. And same with dynamic, you're going to have some static analysis things to help enumerate areas in which to go down and paths to go down so you don't miss them, to make sure you can, get those features in. So I hope that after today, you can go to your reverse engineer and say, help me fix my training set. But yeah, this is some things that I've had to look at over the years, and what I do when I have to verify malware for training sets.